Okay, now we still have one mystery, which is how did we form the gas giant planets? Now remember that the problem, it's a little bit of a chicken and egg problem in a sense, because, okay, so why don't we have hydrogen on Earth? Well, we don't have hydrogen on Earth because it was too hot here. So the escape velocity of Earth was actually lower than the velocity the hydrogen had in this part of the solar system. So Earth couldn't hold on to the hydrogen and it escaped, right? Okay, you get into the outer solar system, it's cooler in the outer solar system, so the thermal velocity of the hydrogen, oh, I should have mentioned, the nebula itself was mostly hydrogen, okay, about 85% hydrogen. So we're talking mostly hydrogen here as the primordial material. Well, we don't see much of it in the inner solar system, but the gas giants are mostly hydrogen. Why? Why were they able to hold on to their hydrogen? Okay, the temperature out there is lower, so the hydrogen is zipping around at a slower speed, but you still have to have something there which has a high enough escape velocity so that they can hold on to the hydrogen. I mean, just because the hydrogen is moving around slowly doesn't just give you a planet automatically. You still have to have a way to bootstrap the process. So we think what happened was that there were turbulent swirls of things occurring in the outer solar system, and those turbulent swirls may have led to the accumulation of an icy mass out there, which then formed basically the icy core with enough mass to hold on to hydrogen. Once you reach that critical mass, then that icy large nucleus, now we're not talking about Pluto here, we're talking about something a lot bigger than Pluto, with enough gravity to hold on to some hydrogen, it starts sweeping up hydrogen because it's able to actually hold on to it. So we have this vacuuming effect, this sort of gravitational vacuum. And eventually, that's an eddy up there that signifies where Jupiter is roughly, we're going to accumulate successfully a lot of the hydrogen gas into the gas giant planets. So we have these kind of primordial, very large icebergs floating around out there in this model. And eventually we get the regular type of pattern that we see. Now, on top of the regularity, there's also fragmentation. All kinds of crazy things happen, for sure. Almost anything you can think of probably happened somewhere along the line. Like these icy planetesimals, there's probably millions of times when they form something that we would think of as a planetary body, only, a grand, spectacular planetary body, only to have an incredibly violent collision and get completely blown apart again, right? So we're talking about fragmentation playing a key role in the buildup and breakdown of bodies until finally we have a few regularly spaced bodies that correspond to the planets that we see today. Computer simulations actually confirm that this model will give you a distribution of planets with dense terrestrials near the sun, massive gaseous planets farther from the sun, but you've got to be a little bit clear about this. I'm not saying that anybody has a program where when you hit enter, it's going to actually spit out exactly the solar system we see. That's really not possible because we don't have enough details about what the initial configuration of the gas was. But we get pretty close, and we figure that's probably enough so that we can be pretty sure we understand the basic physics of the formation process. Probably was a pretty quick process, only about 100 million years, followed by a full billion years of bombardment by the leftover material. This is the period of time when the islands were getting bombarded on the moon, for instance. That's why the islands have so many craters, because they were already solidified during that billion years of bombardment. Around the end of that period is when the Marius solidified and we actually see so many fewer craters. Okay, so we get variation in temperature from the sun. It's going to cause the differentiation where we have the dense material close to the sun, icy material farther away. So here's a curve that actually shows us the temperature. Where's my laser pointer? Well, there's a curve. We see there a blue curve. That's the curve of temperature in the primordial solar system, how it varied with distance from the sun. If we were to plot the curve today, it would not look like this. It would be much lower temperatures at all radii if we could plot the curve today. This is the curve billions of years ago. And what we find is that the distance that Earth is there, same distance Earth is today, we're not going to have ices, we're going to have metals and solid silicate material. As we get farther out, we're going to have water ice solidifying right around the distance of Jupiter, around 4.5 astronomical units. Farther out, we get ammonia ice. We're talking about Neptune and the outer planets. And so this is the curve that actually explains differentiation of the solar system. Dense stuff near the sun, icy stuff farther away from the sun. Okay, so I've just been going just a little longer to try to get somewhat caught up on this. So we see in the outer solar system, the temperature is only about 200 kelvins. If we read off that scale, outer solar system, around 200 kelvins. That's cold enough that we're actually able to form these ices I just mentioned. Ammonia ice, methane ice. We're able to get that iceberg core that we need, that critical mass that we need to get the hydrogen envelope that actually leads to the formation of the gas giant planets. So that could never happen in the inner solar system because you're not going to get those huge icebergs. You've got to be out around the orbit of Jupiter or so to get those ices that you need. So what we have is massive enough planetesimals out there that can accrete hydrogen. We also have lots and lots of icy planetesimals which interact with Jupiter and get flung outward to the Oort cloud, which we've already talked about. And we also have icy leftovers, like very similar to things in your freezer probably. Icy leftovers that are still in place in the Kuiper belt. But a lot of them, again, were flung into the outer solar system. Interestingly, not all of these icy planetesimals were necessarily flung out to the Oort cloud. Some were actually flung in and probably played a crucial role in supplying Earth with water in its early formation history. Because remember, it was too hot on Earth to have water and hydrogen and stuff. So we think that it may have actually been delivered by cometary impacts later on after Earth had actually solidified and it wasn't molten anymore. Okay, our Kuiper belt objects. Again, we found some objects larger than Pluto. Already talked about this. Pluto and Charon, pretty much talked about that. Okay, this is the last slide I want to show today. Formation of the terrestrial planets. This is following up on the comment I just made a moment ago, where we have icy fragments that fly by Jupiter. Now, Jupiter's strong gravity is going to accelerate them and distort their orbital direction. And depending on the exact, precise details of each of these interactions, you're going to get an icy fragment that might fly out or might fly into the inner solar system. And some of them, again, probably represent the formation of the deposition of water on Earth.